Welcome all. Today we are going to start a new chapter, that is fourth chapter in this subject, electronic device and circuits subject, that is C18 third sem subject both for EC and EIE students. Subject code is 303. Topic of the chapter is oscillators, and these are the subtopics in this chapter. So we will see one by one. First, state the condition for an amplifier to work as a oscillator. What do you mean by an oscillator actually? An oscillator will oscillate and produce oscillations. That means it will produce the output waveforms. So from where this oscillator concept come? That is from the basic amplifier itself. That is the tuned amplifier itself. The essential conditions for an amplifier to work as an oscillator are: the feedback applied to the amplifier must be positive, and the loop gain A beta must be equal to unity. If you remember from the feedback amplifiers concept, we have basic amplifier gain as A and feedback factor beta. So the overall loop gain will become A beta. So for an amplifier to work as an oscillator, the conditions, what are the essential conditions to work as an oscillator means feedback applied to the amplifiers must be positive. So positive feedback. You can remember from those feedback amplifiers topic, there are number of applications for negative feedback amplifiers, and most widely used amplifier is also negative feedback because of its inherent advantages compared to the positive feedback. If you can remember, what are the advantages, most advantages in negative feedback? That is stability. Good stability is an important factor. But in case of positive feedback, though it increases the gain, but the stability is lesser compared to negative feedback. So how that should be sustained in order to produce oscillator? Because these two conditions has to be met. The loop gain must be equal to unity is another condition. So the overall voltage given to the positive feedback amplifier is given with the expression AF is equal to A by 1 minus A beta. You must have remember this formula from those lectures. AF feedback gain, overall feedback gain, is equal to A by 1 minus A beta, where A is the open loop gain and A beta is the loop gain. As it is a positive feedback, we will get in the denominator, that is 1 minus A beta. So we know from the essential conditions that the loop gain A beta is equal to 1. What happens when A beta is equal to 1? If you substitute A beta is equal to 1 in the given formula, then what you will get? AF is equal to A by 1 minus 1. 1 minus 1 will become 0. A by 0, something but 0, it is equal to infinity. So AF will become infinity. That is, gain with feedback will become infinity. Then mathematically the closed loop gain becomes infinity. Practically this is not possible, right? Anything with infinite gain is not possible. But what happens in this case? The circuit starts oscillating and stops amplification function. this case, the amplification, the gain is equal to infinity will not happen. But if the input is 0, that means without any input, if we get an output, then the gain will become output by input, that is equal to infinite. But here, nothing input means there is no AC signal input, but we are giving the bias signals VCC, VBB, right? If you remember, right? So with the input DC signal, that is converted into the oscillations. So in other words, when AB is equal to 1, the amplifier works as a oscillator. Now see the practical definition of oscillator. The oscillator may be defined in any one of the following 4 ways. It is a circuit which generates an AC output signal without requiring any externally applied input signal. Right? From the formula, if you can see, that is output is we are getting the output oscillation but without any input. It is zero input, so we will get the gain as infinite. So it is a circuit which generates an AC output. Oscillations means they are time varying signals, so that's an AC output without requiring any externally applied input signal. We are not applying a external input signals, but we are applying the DC bias signals, but bias DC signals. Better not to call it as a signal, DC bias voltages. Or next definition is it is a circuit which converts DC energy into AC energy at very high frequency. At very high frequencies. It is a circuit which converts DC energy into AC energy at very high frequency. We have seen this concept that is conversion of DC energy into AC energy in case of power amplifiers. There the frequency is less, only power frequencies, that is up to 50 Hz maximum. But in case of oscillations, we will get higher frequencies, that is in megahertz, right? Kilohertz to megahertz, gigahertz even possible. Next definition, it is an electronic circuit that generates oscillations of desired frequency. Desired frequency means we can choose the output frequency, that is by adjusting some knob, that is the adjusting some component value, we can change the output frequency, that is in our hands. So that's how we will get desired frequency. You would have seen this practical oscillator circuits in your lab, where usually the name of these oscillators are function generators, right? Where we get the output, it's a function, sine wave function, square wave, right? And different waves we can get. It is an unstable amplifier. It is also called an unstable amplifier because it does not have a stable point where at a particular point it won't stop. It's keep on oscillating. Or the voltage gain, you can see stability comes from the finite values. We are getting here infinite, the gain is infinite, so that's not a particular value. We should have defined it. Next, comparison between an amplifier and oscillator. What is the main difference between why we call a particular circuit as an amplifier and here we call it as an oscillator? Many electronic devices requires a source of energy at a specific frequency which may range from a few Hz to several megahertz, right? In the lab you would have seen those circuits function generators are used in every experiment because we need a constant or desired frequency input waveform to be applied to a experiment, to a circuit, to get what the circuit does. That means how it is changing, how any value changing, what is the frequency response. But in order to get these all practical values, we need some simple input waveforms. It should be constant. There should be some particular necessities for a particular circuit to be used as a function generator or oscillator, right? So in the lab, we need a function generator for every application, for every experiment. We will give some input. So this is achieved by an electronic device called an oscillator. An amplifier produces an output signal whose waveform is similar to the input signal, but whose power level is generally high. So definition of amplifier: yes, we are giving some input signal and we are getting the same input signal with the amplified version, that is the higher power level. That is an amplifier. The additional power is supplied by the external DC source. Hence, the amplifier is essentially an energy converter, that it takes energy from DC source to DC source and converts it into AC energy at signal frequency. This is actually happens in the amplifier. The process of energy conversion is controlled by the input signal. If there is no input signal, there is no energy conversion, and hence there is no output signal. In case of amplifier, this signal whatever we are applying, that is the basis for this energy conversion. But what happens in case of an oscillator? An oscillator differs from an amplifier in one basic respect. That is, the oscillator does not require an external signal either to start or maintain energy conversion process. This is important line, because in an oscillator we don't apply any input signal, external signals. In the lab you would have seen that you just plug it in the power socket, the frequency function generators cable, and you just press the power button, right? You don't give any input signal, external signal from another function generator or small whatever it is, but we are getting the output is, right? We are just giving the supply. So it does not require any external signal either to start or maintain energy conversion process. It keeps producing an output signal so long as the DC power source is connected. The power source, whether it is an AC or DC, because in portable function generators, where generally we will have the portable function generators also. There we have the DC source. A battery will be there. If you keep the power on, then it will produce the output waveforms. So whether it is an AC signal from your home or in the lab socket power line, or it is a battery DC, portable DC battery, if you apply it to the circuit, then it will give the output oscillations, produce the output waveforms. The frequency of the output signal is determined by the passive components used in the oscillator. Passive components means generally are resistors, inductors, and capacitors, not the active components like transistor or diodes. So the frequency we can determine from these passive components. But in the case of amplifier, the amplification is done by the active components itself. So this is a block diagram. If you can see, that is, in an amplifier you are giving the input signal, and the amplifier amplifies the signal and you will get the output signal. Along with the DC input, we are giving the input signal. But in case of oscillator, we are not giving any input signal, but we are providing the DC input to power the circuit, and we are getting the output oscillations. This is the main difference between an amplifier and oscillator circuit. In case of amplifier, we are giving input signal along with the DC power input, and In case of oscillator, we are not giving any input signal, but we are getting the output oscillations. The requisites of an oscillator. What is the conditions to be maintained to function a circuit as an oscillator? Because to maintain the oscillations, generally in the lab, if you have seen the function generator, it produces continuous waveforms. The desired frequency, if we change the frequency also, it will produce continuously without any distortions, and it should be produce the same shape, same frequency without any phase delay for as long as the circuit operates. That means it is applied to the external circuit, another circuit, so it has to be maintained very constant, these values, frequency, amplitude and phase. So in order to maintain such factors constant throughout its operation, we need to maintain certain conditions. Those are the requisites here. The requisites means a thing that is necessary for the achievement of a specified end. Here shows the block diagram of an oscillator. The essential parts here. Tank circuit, functionally the LC, parallel LC circuit, is also called a tank circuit. It is applied to a transistor, and the feedback signal is applied again to the tank circuit. Essential parts are tank circuit, transistor amplifier and feedback circuit. What do you mean by tank circuit? From the previous lecture, you can know, if you can remember the tank circuit, that is, it consists of an inductor in parallel with a capacitor. It is also known as frequency determining network. The values of L and C determines the frequency of oscillations produced by tank circuit and is given by F is equal 1 by 2 pi root LC. F naught we can calculate as resonant frequency. F naught also. In L is the inductance of inductor or coil, inductance value. C is the capacitance of the capacitor. Note, in RC oscillators, inductor is replaced by resistor. We will have RC oscillators also. In that case, the L is replaced by R. Now see the block diagram. We have tank circuit followed by transistor, amplifier and a feedback network. A transistor amplifier, what will it do? The oscillations of tank circuits are fed to the transistor amplifier. It amplifies the oscillations produced by tank circuit, right? But you may have some doubt, but we don't use any input signal in case of this oscillations. Then where this tank circuit oscillations will come? Because the oscillations of tank circuits come from the DC source itself. If we apply the DC source once by opening this tank circuit and apply the DC source to this tank circuit, then the capacitor will charge to its full capacity. Then if we close that circuit by cutting the input DC energy, whatever it is stored to the capacitor, it will start discharging, and the same discharge voltage is applied to the inductor because it is in a closed loop. The discharge voltage will be stored as induced energy in case of inductor in the opposite direction, that is positive and negative, because it's a DC source. So whatever it's storing in capacitor, the reverse voltage, that means the negative voltage, will be applied to the inductor, and then as the time continues, whatever the stored energy in the inductor will also start discharging, and the same discharging current will pass through the capacitor, and the capacitor will start again charging. This will continue, the discharging of capacitor and charging of inductor. The discharging of inductor and charging of capacitor will continue, and this produces a smooth waveform, that is positive off cycle. If it starts to maximum sinusoidal wave, it will produce a sinusoidal wave. and by adjusting some values we can get other waveforms also. Or if we apply the same sinusoidal wave to some diode circuits or clipping circuits, we can get the required shape. So for this particular oscillator circuit, the tank circuit is getting that energy from the feedback of the amplifier. But the same feedback is applied to the tank circuit. The tank circuit will produce the oscillations. The transistor amplifier will amplify these oscillations to the required level. So this is a closed loop network. We are not giving any external signal as in case of practical basic amplifiers and power amplifiers. There is no VS here, source voltage here. So the next point is it amplifies the oscillation produced by tank circuit. Now see the feedback circuit. Its function is to supply a part of the output energy to tank circuit in correct phase. That is in phase signal. It should be in phase signal because the output of an oscillator should be continuous waveform. There should not be any out of phase signals after one cycle. The phase should not change. It should be in phase, then it will be a smooth waveform, continuous waveform with oscillations with particular time period, frequency. All those things will come into effect. So the whatever the feedback circuit we are designing in this oscillator circuit should produce in phase signal with the tank circuit. The amount of energy fed back to tank circuit sufficient to meet I square or losses in the tank circuit. The amount of energy feedback to the tank circuit sufficient to meet I square or losses in the tank circuit. Yes, there is some losses in the I square R because though it is a continuous circuit, that is the closed loop circuit, the capacitor and inductor, it is not infinitely produces the oscillations because in practical components there is some losses, resistive component, resistive effect of this capacitor and resistive effect, thus tank circuit also will come into effect, and because of resistance the current I into R voltage produces and the power loss P is equal to I square R losses also will be there. So after certain time the voltage whatever we apply to this tank circuit will become zero, will keep on discharging, decreasing and become zero, but it should not happen in an oscillator circuit. That's why we produce a feedback circuit. So in order to maintain that whatever we are losing the power because of I square R, it should be compensated by this feedback circuit. So feedback circuit will do two things here. It should produce an in phase waveform with the correct phase with tank circuit, and it is also compensate this I square R losses. The amount of energy feedback to tank circuit sufficient to meet I square R losses in the tank circuit. So it provides a positive feedback. It should be in phase, so positive feedback. There is no loss of signal. It is adding the signal. Now these two conditions, whatever we have seen in the earlier slides, that is the basic condition for sustained oscillation, that is A beta is equal to 1, right? Those are the conditions are called Barkhausen criteria. Barkhausen criteria in oscillators. The basic conditions for sustained oscillations are the magnitude of loop gain must be equal to unity, that is A beta should be equal to 1, and the total phase shift around the loop must be equal to 360 degrees or 0 degrees, that is in phase. In other words, the feedback should be positive. The above two conditions are called Barkhausen criteria for sustained oscillation. This is very important conditions. They will come in competitive exams and interview questions also possible from this area. Okay, so A beta must be equal to 1, that is the magnitude of loop gain must be equal to unity. The total phase shift around the loop, that is from the transistor amplifier to the feedback and to the tank circuit. The overall phase should be 0 degrees or 360 degrees, multiples of 360 degrees. That is in phase. Signal should be in phase. It may be noted that if a circuit does not satisfy any one of these conditions, the oscillations will not be produced. See this here. Why they are called essential conditions? Because if any of the condition is failed to meet, we will not get a continuous oscillated wave. We may get the damped oscillations or out of phase. One cycle will be perfect and another cycle will be reverse of the first cycle, or it will be some zigzag. You can see from the practical experience if you do not maintain such conditions. In every practical oscillator, the quantity A beta is slightly greater than unity. This is practical. Actually, we mentioned the Barkhausen criteria, that is theoretical. But in practical, A beta is not exactly 1. That is, it should be slightly greater than unity. In practice, the loop gain AB is a complex quantity. For getting oscillation, we have to state two distinct conditions. That is, A beta real should be 1 and A beta imaginary should be equal to 0. In practical, the loop gain A beta is not a real number. It is a complex number. It will have real and imaginary both parts. So, in order to maintain the oscillations, we will have condition, that is A beta is equal to 1, which is actually written as A beta real is equal to 1 and A beta imaginary should be equal to 0. Thus, the essential conditions for the maintenance of oscillations is A beta is equal to 1 plus J0, complex quantity. So, 1 plus J0 there, magnitude A beta is equal to 1 and the phase angle A beta is equal to 0 degrees or 360 degrees. Phase angle tan inverse y by x 0 by something tan 0 0 degrees. So the condition that the imaginary part of the loop gain should be equal to 0 gives the relationship that controls the frequency of oscillation. The condition that the imaginary part of the loop gain, that is imaginary part J0 condition, gives the relationship that controls the frequency of the oscillation. The condition that the real part should be equal to plus 1 indicates the amplitude of the oscillation. So the real part consists of the magnitude and the imaginary part is consists of the frequency. As we know, A beta, that is imaginary number, complex number, sorry, real plus imaginary, that is complex number. We can remember from the mathematics that x plus jy can be written as magnitude and angle phi, where magnitude is equal to under root of x square plus y square and theta is equal to tan inverse of y by x. So that's why it is a magnitude, and the magnitude corresponding to the amplitude and the theta angle corresponds to the frequency. Now moving on to the next topic, that is classification of oscillator circuits. The oscillators are classified based on the nature of the output waveform, circuit components, range of frequencies, etc. These are different classification. Based on these conditions, we can classify based on these parameters. The various ways in which oscillators are classified are according to waveform generated. First one is according to the output waveform, right? So according to waveform generated, that is sinusoidal oscillators, sinusoidal, non-sinusoidal. In the sinusoidal itself, we have different classifications again. According to the type of the circuit used, sinusoidal oscillators are further classified as first, classification of oscillators based on the output waveform produced. In that we have sinusoidal and non-sinusoidal, and again in the sinusoidal we have different types classification based on the type of circuit used to produce this sinusoidal waveforms. First one is LC, inductor and capacitor oscillators. LC oscillator simply. In that LC oscillators we will have tuned collector oscillator, tuned amplifiers, Hartley oscillator and Colpitt's oscillator. And from the previous lesson, if you can remember that these are tuned amplifiers. Tuned amplifiers will produce the oscillations, but we have concentrated more on the frequency response only in the previous lecture. And second one is RC oscillators, resistor and capacitor oscillators, RC phase shift oscillator and Wien bridge oscillator. And third one is crystal oscillator. So what are the different type of circuit we use it to produce these sinusoidal waveforms in the output circuit? Then classification is happen here, that is LC, RC and crystal oscillator. Now in case of non-sinusoidal oscillators, that is multivibrators, sweep circuits and blocking oscillators, they will produce non-sinusoidal waveforms. It is like square waveform, triangle waveforms and other things. Next, according to frequency generated output, we will have the oscillations, right? So particular waveform, any waveform, AC waveform will have a frequency. So depending on the output frequency produced by these oscillators, we can be classified these oscillators into different types. That is, first one is audio frequency oscillators, that is AFO. That is up to 20 kilohertz in the audio frequency range. Range of frequency is up to 20 kilohertz. Next, radio frequency range oscillators, RF range, that is 20 kilohertz to 30 megahertz. Very high frequency VHF oscillators, 30 Hz to 300 megahertz. Ultra high frequency UHF oscillators, 300 megahertz to 3 gigahertz. Microwave oscillators, that is above 3 gigahertz. According to fundamental mechanisms involved. So next classification is based on the fundamental mechanisms involved, that is negative resistance oscillators and feedback oscillators. So according to fundamental mechanisms involved, negative resistance oscillators and feedback oscillators. In the basic block diagram, we have seen the feedback oscillator. We use the positive feedback here in the introduction part of this topic. We have seen that is a feedback oscillator, but we can use another mechanism, that is negative resistance concept of negative resistance oscillation. Yes, there is a possibility of negative resistance, not the negative resistor. It's a resistance. This property from a particular circuit, you can get this concept of negative resistance, but there is no negative resistor. Classification of oscillator, if you summarize into this, that is first sinusoidal oscillator, the oscillator which provide an output having a sine waveform are called sinusoidal or harmonic oscillators. Typical example of these oscillators are, you didn't give any oscillators. Now non-sinusoidal oscillators, an oscillator which provides an output having a square, rectangular, sawtooth waveforms are called non-sinusoidal or relaxation oscillators, because the relaxation oscillators are produced from relaxation circuit. And third, RC oscillator, the oscillator using the components resistors and capacitance are called RC oscillators. LC oscillator, the LC oscillators using the components inductance and capacitance are called LC oscillators. Note, the RC oscillators are used at audio frequency range while the LC oscillators are used at radio frequency range. So the components used we use to produce the oscillator that is in the tank circuit we use, or if it is an RC, the output frequency range will be in the audio frequency range that is up to 20 kilohertz. But if you use LC, inductor and capacitor oscillators, then we will get the frequency in the RF range, radio frequency range that is greater than 20 kilohertz. Crystal oscillators. These oscillators use quartz crystal and are used to generate highly stabilized output signal with frequencies up to 10 megahertz. This is important. Why we use crystal, that is quartz crystal, are used to generate stabilized, highly stability output signal with frequencies up to 10 megahertz. Next, feedback oscillator. The oscillator in which the feedback is used, which satisfy the required conditions, are classified as feedback type of oscillators. Non-feedback or negative resistance oscillator. The oscillator in which the feedback is not used to generate the oscillations are called or classified as non-feedback oscillators. The non-feedback oscillators use the negative resistance region of the characteristics of the device used. See here in I have explained in the previous slide that the non-feedback oscillators or negative resistance oscillators use the negative resistance region of the characteristics of the device. So particularly UJT, generally we use UJT for this negative resistance concept because in the UJT we have UJT characteristics, we have negative resistance region. The negative resistance means negative resistance region. What will happen in the negative resistance region? If we can remember from the Ohm's law, that is V is equal to I R, that is V is directly proportional to I. As voltage increases, the current increases, then it is called positive resistance region. If voltage decreases with the increase in current and vice versa, then it is called negative resistance. Yes, this type of thing can happen. The voltage increases, then the current can decrease at a particular region of a characteristics of the UJT, junction transistor, in the device, that is you are going to learn in the next chapter, right? In this particular UJT transistor we have negative resistance region, and that can be used to produce oscillator circuits. So today we have learned these topics. Just go and revise. We have less time of about 5 minutes, 5 to 10 minutes. So instead of starting the new topic, just go through the revise what we have learned today. We have started a new chapter, that is oscillators, right? And these are the objectives and subtopics in the oscillators. First one is the condition for an amplifier to work as an oscillator. It's a feedback amplifier. It should be a feedback amplifier. So we have feedback gain AF is equal to A by 1 minus A beta. So the condition to be satisfied to produce an oscillator, because oscillator does not have any input signal, but we should get the output signal. So the gain is equal to output by input. So output is there but input is 0, that will produce infinite gain, which is practically not possible. But what happens here, in case of oscillator, we are not giving the input signal from an external source, but we are giving the DC source, that is bias voltages, that will convert it into AC energy. The DC energy we are supplying for the circuit to bias, that will be converted into the AC signal. This conversion is possible in the power amplifier also, but there we have used the input signal, external source, VS source. Because of that source, this conversion happens. But in case of oscillators, we are not giving an external source. So the condition is A beta should be equal to 1. Voltage, the overall loop gain should be equal to 1. So the gain will become infinity. And the definitions, see different types of definition, but the first one is more accurate and relevant. So it is a circuit which generates an AC output signal without requiring any externally applied input signal. Comparison. What is the difference between amplifier and oscillator? Amplifier will amplify the signal, but oscillator without any input, it will just convert the energy from DC source to AC source, AC energy at that particular frequency. And the frequency we can choose, that is the desired frequency, can be achieved from the by adjusting some component values in the oscillator circuit. So difference of oscillator and amplifier can be understood from this block diagram. That is, for the amplifier we have input signal, we get the output signal by applying the DC input. But in case of oscillator, we do not give any input signal, but we get the output signal from the applied DC input. Mention the requisites of an oscillator. Requisites minimum conditions or whatever the blocks inputs we should give to produce the oscillation, that is tank circuit and transistor amplifier and feedback circuit. From this block diagram you can see that's a tank circuit. The output of the output of tank circuit is applied to the transistor amplifier, and the feedback is given from this output of transistor amplifier to the tank circuit. So there is no external signal Vs is applied here, but the transistor amplifier will amplify the oscillations whatever we are getting from the tank circuit will be amplified. And the feedback circuit does the most important point here, because it should produce a positive feedback that is in phase with the tank circuit's oscillations, and the energy loss, but whatever we are getting the loss I square R from the circuit should be constant. From the tank circuit we are getting I square R losses, but those losses should not uh, distort the output waveform. So in order to maintain the constant output, constant voltage, constant frequency and phase, we should compensate its losses by the feedback circuit. And we have seen the Barkhausen criteria, that is most important, that is AB should be equal to 1 and the loop phase shift around the loop must be equal to 0 degrees or 360 degrees. These conditions has to be satisfied, but in practical we have A beta is equal to 1. That means A beta is a complex quantity in case of practical. So A beta will have two components, that is real component and imaginary component. So practically speaking, A beta is equal to 1 means A beta real should be equal to 1 and A beta imaginary should be equal to 0. From the complex numbers we can write magnitude A beta is equal to 1, and if it is 1 plus j0, then the phase angle A beta is equal to theta is equal to tan inverse of 0 by something tan inverse 0, that is equal to 0 degrees. So the condition that the imaginary part of the loop should be equal to 0 gives the relation that controls the frequency of oscillations, and the condition that is A beta real part is equal to 1 decides the amplitude of the oscillation. So this from the A beta we get the amplitude and frequency, which is the most important uh, points to be considered in the output waveform. That is frequency and amplitude both should be constant to be maintained throughout the experiment. Next we have seen different classification of oscillator circuits, but is based on output waveform. We have seen sinusoidal oscillator or non-sinusoidal. In the sinusoidal itself we have different classification based on the type of circuit used, that is LC, RC and crystal oscillator. LC we have tuned oscillator, tuned collector and Hartley and Colpitts. RC we have RC phase shift and Wien bridge, and crystal oscillator. Non-sinusoidal we have multivibrators, sweep circuits and block circuits, blocking oscillators. Multivibrators will produce square waveforms, sweep circuits will produce the triangular waveforms, blocking oscillators will produce also triangular. And according to frequency generator, that is up to 20 kHz you have radio frequency and 20 to 30 megahertz radio frequency, above 30 megahertz to 300 very high frequency, and 300 megahertz to 3 gigahertz, that is ultra high frequency, and microwave oscillators are this above 3 gigahertz. According to fundamental mechanisms involved, we have negative resistance, oscillator and feedback. So we have learned about feedback oscillator, but this concept of negative resistance can be obtained from the UJT, it is unit junction transistor in the characteristics of this UJT will have the negative resistance region, which will be used for the produce oscillators. That is, if the voltage increases and with the decrease in the current and vice versa, then that is called the negative resistance region. And we have crystal oscillator, that is quartz crystal is used to produce highly stabilized output signal with frequencies up to 10 megahertz. So RC oscillator is used for audio frequency and LC for radio frequency. So with this we complete today's topics, that is introduction of oscillators and the conditions to be maintained. And in the next class we will see different oscillator circuits, how they will produce the oscillations, what are the advantages, disadvantages of those circuits, right? So if you have any doubts in these topics, please mail me at sureshakul2001 @gmail.com. If you want to refer further topics, just Google the electronic device and circuits book by Jacob Melbourne, that is the standard book. If you can refer any other standard book also, right? Thank you. I'm closing the session now.